Perfect. All right, let's go. Welcome again. This class is going to be about statistics. As you can see, I'm math dressed for the occasion. Okay. What are we going to learn today, and why are we going to learn it? Because as you have probably noticed, we have entered the information age, and where there is information, there is like lots of data. Okay. I'll be back in frame in just a second. There's like lots of data. And when you have lots of data, do you wonder what's the mathematical branch that analyzes the relation between lots of data and the logical, or at least the formal methods to reach conclusions based on lots of data? Well, that branch is statistics. So statistics, I mean, it's always been important. Math is important to just understand reality and each other better, more specifically physical reality and stuff like this. But the thing is that in the era we're getting ourselves into, the era of information, understanding statistics is pretty much an essential thing you want to do if you want to go farther with all the data. If you want to discover more truth, more useful knowledge, you must know statistics. And this is not going to be a mathematical class. There's not going to be much math here. It's going to be pretty simple. It's going to be more of a development of intuition of what good statistics. Good is not a good term for mathematics. What correct statistics looks like. And I gathered 9 statistical principles that everyone should at least have an intuition for them, in order to be able to discern between illogical conclusions in some statistical studies and logical conclusions. So, as you might have noticed, all the science, all the papers on science and stuff rely on data and statistical deductions or inference. I don't know how to pronounce that now. Of stuff from the data. And when you do a lot of studies, if all of them say the same thing with similar statistical behaviors, blah 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 blah, we consider that a new scientific truth. So it's important, right? And also, as you might have seen, some politicians cite studies, or politicians, or whoever is trying to make a point about something, and they cite studies, but the studies were not properly made. Oh wait, this was charging the whole night. Why doesn't it have battery? It was charging the whole night. Okay, Capybara is off. So we're gonna take Master Shifu instead. So that's the thing. Like, if you want to be able to think with a more versatile way, to make even more interesting questions that can be more useful, you must understand statistics, especially nowadays. And if someone says, classic example, no, immigrants are a problem and they increase criminality. Well, if you're gonna state that, you better look at the statistics and see if that's actually true or not. I'm not gonna get into the specifics if that's true or not. It will depend on the country, or maybe it doesn't. You need to gather the data and check it out. Some people might say, for example, okay, let's start with the drama. Let's start with the drama example. In Spain, here in Barcelona, I think it was a few years ago, there was a study that said 80% of the criminals are immigrants. Therefore, immigrants cause crime. That's illogical. That doesn't make sense statistically, and we will see why there. With only that data, you cannot conclude that immigration leads to crime. You would need more data. Why? How can you feel sure about that in a logical way? Well, I'm gonna give you 9 tools, 9 statistical concepts that you will be able to understand intuitively, and you will be able to use in order to judge the data for yourself and to debate or at least share information and insights with other humans so you can actually reach the truth. And with more data and more information, you can well solve problems like the allegedly immigration problem. I know this is controversial, that's why I'm starting with it. I wanted to put it at the end, but or another thing, sexism, another controversy. Is actually sexism being so predominant in our nowadays culture? Like, how was this? 80%, something, I don't know. I don't know. I'm gonna make it up, but the discourse goes like 85% of the people who rape are males, therefore males are rapists. Is that true? Is that not true? Is that a logical conclusion? An illogical conclusion? Where did you take the data from? How did you take the data from? How it should be done in a logical and coherent way? That's what you're going to learn. I'm not going to give the answers to the immigration problem or the sexism problem. Maybe they are problems, maybe not. That would be your homework if you're interested. Or any other. I mean, before this homework, I'm going to put another homework that is more important, more fundamental. So let's start. Let's start understanding, okay? These 9 concepts. I think I explained everything, right? Why is it useful? What we're going to learn, and what is what we are going to learn. But first, let me tell you, free resources online, statistics. Sorry, statistics has been around for hundreds of years, so there's lots of information online. Just check it out. The MIT courses. That's a university that gives free courses online. You can check that out. There's also paid stuff like Brilliant. That's just another platform that you have to pay for that. Of course, they guide you, they make it fancy, and it might be helpful for some of you, but you have to pay. That's the downside. Also, Math Academy. Math Academy is another thing that you can use to learn math, but you have to pay. I recommend talking to ChatGPT or watching YouTube videos about the concepts. I'm going to create a general map of all the important concepts for being able to have a more rational discourse and more rational and according to reality decisions. So let's start with the first concept. Sorry, Shifu, I'll move you behind the capybara. Statistics. Statistics. Bada bim bada boom bada bim bam boom. Bum bim bum boom boom. I hope this little song didn't have copyright or existed somewhere, because I just made it up. Bada bim bada boom bada bim bam boom bada bim bum 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 boom. Oh, not bad, not bad. So first, let's start the understanding of 3 very important statistical concepts, which are kind of the base, I would say. But the green is not working very well. I'll use the blue. Let's understand the difference between the mean, okay, the median, and the mode. These are different, okay? The mean is usually known also as the average. Or if you're gonna get fancy and technical, you can say the 50% percentile. I'm not gonna explain this of the percentiles. I think I'm not gonna explain that. But if you are curious about it, talk to ChatGPT about it. Tell him, hey, can you explain this to me in very simple ways? Or you say, use the Feynman technique and explain this to me. That's a very, very, very cool technique. The Feynman technique, which is basically, this was invented by Richard Feynman, a physicist. And, well, I don't know if he was the first inventor, but it has his name. Which is, you first talk to the student, you explain him some stuff, and then you see the gaps in the knowledge of the student and you try to fill the gaps. Tell ChatGPT to do that for you. ChatGPT or any other AI, I don't know. OpenAI is not sponsoring this video. So yeah, you can just go ChatGPT and understand the concept of a percentile, which is going to be useful, but it's not so essential. Let's start with the more basic things like this. What is the mean? The mean is like the average value. Okay, if you have, let's say that you are measuring trees, and one tree was 10 meters. The other tree, let's say we have 5 trees. All of them are 10 meters. Okay, what is the average? Well, it's the 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 most common. No, that's not the way. Well, you basically add everything up, 10 plus 10 plus 10 plus 10, and divided by the number of data samples. This time we have collected five data samples. So that means this is 50 divided by 5. We see that on average there is 10 meters. But that doesn't mean that if we generate a random tree right now, it will be measured. It will be likely 10 meters. That's not the logical conclusion you can make out of that. Because let's give I think I have the rich people example. Exactly. This is a classic example. Imagine you have a country of 3 people. And the first person makes 10K a year, 10K dollars or euros, whatever. The second one makes 10K, and the third one makes $1 million a year. What is the average? Well, you add all this, 120 divided by 3. I mean, I know it's like, must be like 40K, but let's make it exactly 40K. So you say that in average, if we generate a random citizen here with the actual statistical chance of salary distribution, he will have 40K. Well, we don't know. The sample is too small. And actually you see, oh yeah, the average is 40K, but that doesn't really represent 10K. 40K is pretty different from 10K, and it doesn't even represent $1 million, because 40K is way smaller than $1 million. Oh, wait. I'm missing a 0. This is not, sorry. This is 1,020K. So this is 1,020. Okay, sorry, it was actually even worse. It's 340,000. Okay, that's the average, which is very far away from here and very far away from here. So we can see that the average is not a good representation for some kind of deductions. Like, oh yeah, no, usually people in this country earn this much. Well, not really, because it's biased. The sample is biased. There's an over-representation. Well, we cannot actually conclude that, but I hope you start to see the idea. And how would you get an intuitive sense on what's the average, right? Like, well, what the average is telling you, the mean, is that if all the things we have measured were to be evenly distributed with all the participants in the measurement, how much would each participant get? That's what it tells you. Nothing else, nothing more. I think, if I'm not wrong. So if we had to add all the height of the trees and then distribute it evenly through all the trees, each tree would get 10 meters. If we added all the wealth of this country and distributed evenly to each citizen, each one would get $340,000. But that doesn't mean that the most frequent value is $340. In fact, there is no one with $340. The most frequent value is what is called the mode. In the trees example, it was 10, right? So let's give another more abstract example, right? If we do different measurements and we have this set of numbers, 5, 6, 6, 7, 1, 3, I don't know, dick sizes, to make it more funny and more relaxed, because this is a bit of a unit focus to understand math. So let's make it more relaxed with some sexual humor that everyone understands. So what is the mode of dick sizes in this set? Well, it's 6 because it appears 2 times. It's the most common value. Because 5 appears 1 time, 6 appears 2 times, this appears 1 time, 1 time, 1 time. So the mode is 6. What is the mean? If we add all the dick sizes and we distribute the dick size evenly in the population, what is the mean? Well, it's 5 plus 6 plus 6 plus 7 plus 1 plus 3, which is just the total centimeters of dick length we have in society, which is like 10, 11, 17, 24, around 29. Then you divide by how many people: 1 dick, 2 dicks, 3 dicks, 4 dicks, 5 dicks, 6 dicks. 29 divided by 6. That should be around 4.83. Oh, yes. 4.83 periodic, but let's forget about the periodic. We don't really care about this detail now. If you don't know what periodic means, it just means it goes on forever. There's just infinite number of 3s behind the comma. That's what this thing represents. Man, the intuition. I nailed it. Yeah, I'm not used to mental calculus because I'm a software engineer. I always use computers and programs to calculate. Anyway, so for each citizen, we would give him 4.83, let's say, centimeters of dick. Very long. So that's what the mean would be, the equal distribution of all the measured things. The mode is the most frequent measurement, and median in the data set, okay, in all the data we have collected from every observation. And the median, it means the value, if we arrange all the data from smallest value to greater value, the one who is in the middle, that's the median. Why is that useful? I'll show you now. Let's go with dicks, and then I will use another example because I'm getting tired of dicks. Let's order everything. Okay, the smallest is 1, the next is 3, then we have 5, then we have 6, 6 and 7. This is the ordered value of the data. Now we take the one in the middle, which is like, we can see it visually. It's uneven. It's even, so there's no middle values you can see, but it would be something between 5 and 6. Usually what you do when this happens is you take, let's say, the middle point, right, between 5 and 6. Okay, this is too advanced, you don't need to understand it, but between 5 and 6 there is 5.1, 5.2, 5.3. So you take the middle of the middle, 5.5. So the median here would be like 5.5. That's usually what you do when you get this. If the data set is even, okay, sorry, uneven, let's say someone has a dick of 8 centimeters, then it's pretty simple. This is in the middle. So you can see there is 1, 2, 3 away from the end, 1, 2, 3 away from the beginning. This is in the middle. The median will be 6. But this only happens when the amount of data you have collected is an odd number. In our case, we had an even number, so you usually do stuff like this. Maybe in some data sets you don't really want to do this, but I think that's like the formal definition of it. Anyway, you get what I say. It's the one in the middle, okay? The one who splits the data observations in half. That means that half of the data is smaller than this and half of the data is greater than this. So if we know that the median of dick sizes in a population is 6 centimeters, we know that half of the population has a dick greater than that and half of the population has a dick smaller than that, which is 50%. So that's the logical conclusion you can take from this data and be correct. You can say, oh, 50% of the population do have I mean, maybe it's 51% because it's would be like greater or equal. It's not the same greater than greater or equal, but you get the intuition. The thing of this class is not the super specific math formalities, but so you get the intuition and the meanings and the things you can actually deduct from these statistical measurements: mode, median, and mean. For example, if you know that the mode is 6 and you have to guess how long is someone's dick, you are more likely to guess it if you say 6. Because if you say 6, there's 2 out of 7 chances that you guess right. So if you want to guess, you should pick the mode. If you want to have an intuition of how much people actually earn, maybe you should pick the median. Because what's the median salary here? It's 10K. That's a more realistic representation of what most of the people in this society actually earn. But it would be actually, not really, it would be more of a guide, okay, not a truth. Statistics is always about kind of like getting guides to sort of shape truths, but not, boom, concretely defining them. It's running out of water. So these are the differences. And okay, this I will tell you later what kind of questions you can ask yourself to detect incorrect conclusions from any of these things. On average, when someone says on average, they are talking about this, and maybe they are taking incorrect conclusions. Maybe they are talking about the average, but it's actually what they should be using is the median or the mode. So yes, like for example, you can say no. On average, people in this country were making, the calculation was $340,000. So therefore, this country is very rich. We are very rich guys, no? But then you would say like, but bro, like the median is 10K. Half of the population is making 10K or less because it's ordered in an increasing way. So how can you say that a country is rich if they are only making 10K? Yeah, the average is saying that, but that doesn't mean that everyone is making 340K, right? You can see the logical flaw, I hope. And if not, just pause the video, think about it, write it down yourself, maybe talk to an AI, look at YouTube video. I'm not the best one explaining this, but there's a lot of people explaining this on YouTube and stuff like this. For example, the mode. Imagine another conclusion. Imagine this was like 26. Okay, and it's like, oh, the most frequent dick size in our nation is 26. So Spanish people have very long dicks. But if you look at the data, it's only 2 people out of 1, 2, 3, 4, 5, 6, 7. So it's not really a logical conclusion to make only 2 people out of 7. So to pick a trend, you should pick the mode. Maybe, as you can see, and now this leads to another thing, which is the size of the data you have gathered, right? The more data you gather, the more your data will reflect the truth or shape, but not necessarily define the truth. I'm going to explain this in a more intuitive way now, because it doesn't really matter the measurement, but also how many measurements in order to be able to use these statistical tools to better represent reality. So these are the tools: median, mode, and a mean or average. These are the first of the 9 concepts I want to explain. Let's see how much time it took me to explain this so I can get an approximate 24. Oh my god, this video is gonna be so long. Maybe I have to split it in 2. The light is gonna run out of battery if I continue like this. But I'm not gonna rush it. So maybe I just split it in 2. Second, the idea of the spread of volatility of risk in general mathematical descriptions, it's called the variance. Now we're gonna learn or understand what the hell is, it's a bit wet, the variance. The variance. The variance is the distance from any data point to the average. Okay? That's not maybe the best definition. Wait. Yeah, for example, let's go with another data set. Let's go with the trees example. Okay? Length of trees. 10, another 10, this one is 12, this one is 10 again, this one is 12 again. Let's keep it at here. What is the average? 30, 40, 50, 54 divided by 1, 2, 3, 4, 5. 54 divided by 5. 10.83 again? No, 10.8. Oh no, I got it wrong. Yep, 10.8. So the average is 54 divided by 5, which is 10.8. Let's say that this is measured in meters. It's very important. Never mess around with the units. If you measure in meters, compare it with meters. Okay, that's super important. That's another logical inconsistency, but usually scientists are pretty advanced and don't make these mistakes. But I mean, there was one time where one rocket, there is a story, they threw a rocket at space and it blew up because one of the scientist team were using meters and imperial units, and the other ones were using, I think it was inches, like the American units, and everything went to brr and a rocket make boom because they were using different units. Or it was something like, search the story, it's very interesting, like how guys did you mess it up? Motherfuckers. Everyone can make mistakes though. But yeah, like units are important. Rockets can explode literally if you don't really take them into account. So yeah, units are like a language. You both have to speak the same language if you want to understand each other. 10.8. Let's take 12. What is the variance? How much does this value varies from respect the average? So the difference is 12 minus 10.8. That's like 1.2. So the variance, I mean, how fucking now I don't exactly remember I think the variance is the average variance, or that's like the, wait, I have some, oh my god, I have some, oh shit, I don't remember how to properly define variance. Give me 1 second. As you can see, everyone learns, even the teachers. Oh, I knew this. I'm gonna ask ChatGPT. Define variance simply in 2 lines. So my guess is that it's the average of differences from the average. Variance measures how far a set of numbers are spread out from their average. Yeah, exactly. It shows how much the value differ from the mean or average. And is it a per value thingy or a average of distances? Because from the average, because I think that the average of distances from the average, I think has another name, but I'm not sure. Oh no, okay, no, it's true. No, actually, I'm not mixing names. Okay, variance is the average of distances from the average. So this is 1.2. The difference between 10.8 and 10 is 0.8. So we're collecting like another data set, the data set of differences from the average. This is 1.2. This is another 0.8. 10 minus 10. This is 1.2. And now we would make the average of all this new data set. And that would be the variance. Which, I mean, let's compute it. 2.4. 8 times 3, 0.27, 2.7, 2.7, 2.4, 4.4 plus 7, 3.2. I don't know, I don't give a shit. Let's make it like this, it will be faster. 4.8 divided by 1, 2, 3, 5 data points, 0.96. That means that every value on average is 0.96 units away from the mean, from the average. This is useful. I mean, this is getting pretty advanced, and I told you this is not going to be, it's going to be more like intuition rather than formal definitions and stuff. You should actually get familiar with this and play around with exercises and stuff, so your brain gets used to this. Why is this useful? For example, in the stock market, the volatility can be measured as a variance. Let me explain. We know, I hope you know that stocks and different things change in value through time. And this is also important for something we will see at the end. But one of the things is this one, stock prices. You have the chart of a stock. This is time, okay? First year, second year, 3 years, time. And this is the price in whatever, in dollars. And it goes like this. And then, I don't know, it goes down, then go out, whatever. The variance, if you do the average thing, you pick all the points and you make the average, you will get an average price. Let's say that the average price is this value. Let's say it's 3.5. So this would be the line that represents 3.5. That will be the average. And now you will be getting the distance from the average in this point, which is this distance, from this point, which is this distance, from this point, which is this distance. And then you will be doing the averages of all the distances, and then it will be like, let's say that the average is 3, and 3 is here. That would be the variance. What does it tell you? It tells you kind of the average likelihood of of the next price on the next year is how much it will change, kind of. It's some sort of rate of change. But I don't want to get so detailed because that's not the point of this video. But it's nice for predicting or having a sense, an informed decision, professional gambling of where the price is going to move and stuff. That's at least one of the useful cases of this concept. We're going to see another useful case, which is way more useful than this, but at the end of the video. Yeah, like just, the idea of this video is not to make a super mathematical formulation, very precise, very exact. I want you to expose your brain to the information and then get curious and ask questions about data sets that you care about. Like, for example, immigration data, or whatever you care about, or dick size data, or trees data, and how it relates to the amount of CO2 in the atmosphere and if that is creating climate change. I don't know, just take a data set that you like and use the understanding of these concepts to get closer to the truth. Okay, so I'm going to present you the concepts, and then it's like if I'm presenting you the tools. Okay, I'm presenting you the hammer, the screwdriver, the thing that I don't know how is this name. This tool. Do you know this tool? You know this tool? I don't remember. I don't know the name of this tool. I'm presenting you the hammer, the screwdriver, the tool. So later you can go out, gather some wood from a tree or whatever you want to gather the wood from, and build a door, a nice door, which is the knowledge. Okay, so I'm presenting you the statistical ideas and concepts you should be familiar and master to use them in your mind with the data, which in this metaphor would be the natural resources, but it would be like data, and then create actually something useful, like a house or an idea of what's going on in society. So that's the main idea behind this class. It's not like a full mathematical statistics pure class. Okay, so we now now some concepts that you should be familiar and master, like variance, mode, median, average, mean, which is the same, the average and the mean. So that's the second concept. Let's go to the third concept. And now we're going to understand why size matters, why the size of the data set matters. Let's say that I have a coin. Do I have a coin with me right now? There doesn't matter. We have a coin. You know that there is a 50% chance now. If the coin is fair, 50% of the time, around that, it will be heads, and 50% of the time, it will be tails. Now, let's say that we throw the coin 4 times. Okay, we throw it 4 times. And we have heads, tails, heads, heads. And we see, oh, damn. 1, 2, 3, 4. 1, 2, 3. 3 out of 4 times is head. That is 75%. And we can say, okay, because of statistics, I will conclude that throwing the coin has a 75% chance of being head. Well, that's not true. What do you have to do to realize this? Well, just throw it more times. And if you throw it more times, you will eventually realize that it's more like head, tails, head, head, tails, tails, head, tails, head, tails. And this approaches more to reality because reality is complex and chaotic. There can be what is usually known as noise or specific things that happen once. Let's say that you threw this coin in a table with a magnet, which actually was designed to attract the head parts more often. That could be a bias in your data set or in the way you measured it. There can be biases, things that I'm not going to define bias exactly now because it's getting a bit out of topic. But as you can see from this pretty intuitive example of head and tails, it doesn't really matter that you have a fair. Imagine this coin was fair. It had actually a 50% chance, but you only tried it 4 times. And the chance of this happening is not that small. So in order to get closer to the truth, you have to repeat this multiple and multiple times so we can be more confident that the next time we do it is gonna also happen. This is about the principle of if it happened today, it will happen tomorrow. Okay, I can be confident that if this happened today, it will happen tomorrow. And if you only do it one day, you cannot be fully confident in. This depends on the experiment, but this is the underlying principle, the guide, not the truth, the guide. If I want to be confident that every day I throw 4 times a fair coin, there's a 75% chance that I will get heads, I shouldn't just do it one day. I should do it today, should do it tomorrow, should do it tomorrow, should do it tomorrow. And if the if the coin is actually fair, the next day you may get heads, tails, tails. Oh my God, 50%. And then the next day you might get head, tails, head, tails. Oh my God, 50% again. And then the average or or even the mode or even the median or maybe all of them eventually land on 50 or around 50%. And then you can be more sure that tomorrow, if I throw this coin 4 times, there is actually a 50% chance in each independent throw of the coin. Okay, if we get technical, there's a lot of nuances, but I want you to get this intuition. The intuition of that the amount of times you repeat an experiment matters a lot. And of course, it should be under the same conditions. As I said, if you throw the coin in a table with a magnet that somehow favors one side of the coin, and tomorrow you throw the coin in the grass where there's no significant external conditions that favor one outcome, well, then the thing will be brr, brr, brr. So that's something very important. The amount of times you repeat the experiment and that the context and the conditions in which you repeat the experiment are as similar as possible, ideally, they are the same. So if I throw a coin here, this little bar, I throw it here 4 times, and tomorrow I'll do the same. Same conditions, same experiment, same way of measuring it. That's what matters. So that's how it matters. Like in studies, it's not about how many people they have asked something. For example, with imagine you go to the street and you ask literally like the same thing. I think I'm gonna put the same numbers. Yeah, you ask 5 people, and 5 people are gonna tell you, I'm gonna vote for this president, President A, B, 1, 2, 3, 4, and C. And then it's like, okay, so we can conclude that A is going to win the elections because I've done statistics, I've gone outside, I've asked 5 people, and there is a 60% chance that because there's 60% of the people support A, 20% of the people support B, and 20% of the people support C. So it's likely that that A will win because this is the majority. But it doesn't really matter because maybe you went and asked these people, and these people were like the family of the politician. This was his sister, his cousin, and this was his childhood friend. And these people were like actually random people. So if you want to approach truth to reduce the possibility of a bias to fuck up your calculations or your shape of truth and reach actually an more objective truth, you have to increase the sample, and you have to increase it in a varied way. Don't only ask next to the house of one politician because maybe the neighbors get along with him, I will vote him. That's a bias. You should ask in this neighborhood, in this neighborhood, in this neighborhood, and if the population is 45 million people, don't ask only 100 people in one neighborhood. Ask 100 people here, 100 people here, 100 people here, and have a greater data set from different parts under different conditions. Okay, in this case, as you can see, we're doing the experiment under different contexts. And I told you earlier that no, you have to repeat the experiment in the same context. There is different, I mean, how can I explain this? So, because there is not much noise. That's what I said before. When you throw a coin, okay, that's a pretty physics-related experiment, and there is not much factors that could influence the coin flip. Me throwing it randomly, and gravity, and maybe the surface of this, but that's something predictable, I can measure, I can account for. But when you're doing social experiments, there is more noise that can introduce biases, which is just more variables to take into account, like which neighborhood are you doing this? What is the relationship between these 2 people? What is the average income here, or what is the average culture here in this part of the country, in this part of the country, in this part of the country? Are you taking into account a significant part of the country too? So because when you measure, things are more complex in the way that it cannot be measured very accurately. You introduce more probability of noise, of factors that you didn't think about, but they were there influencing the things you measure. So in those cases, maybe you want to change the context. I hope this kind of makes intuitive sense. In other cases, like physical experiments for reaching physical deductions, you don't really care. Actually, you prefer the context to be the same because the noise is more manageable, more predictable. And human relations are something pretty unpredictable and chaotic. There is psychology, sociology that are trying to measure and reach conclusions with all these formalities of statistics. And that's why you also have to understand statistics so you can actually know what's going on when you see a scientist give an argumentation based on statistics. And you can actually say, okay, but is your data set biased? How much noise was in the measurement? Did you measure a decent amount? All these intelligent questions that you have to train your brain for. And there's no other way of training it that every day or every other day you sit yourself, you ask ChatGPT to generate a problem for you, and you solve the problem. Like, for example, ChatGPT, give me a data set and tell me an illogical conclusion about the data set, but it sounds kind of logical, and help me learn fallacies. You can do that. Also, there might be like other YouTube videos somewhere with that example. But with AI, now that we have AI, this is very good. You can train yourself with AI very, very well. And just in case some AI is biased, do the experiment in a different context. Talk to another AI. Talk to ChatGPT, talk to Grok, talk to Claude, talk to all of them. Talk to a person, please. Go to, if you have a friend who is an expert in statistics, ask your friend to just hang out in the bar and try to solve some statistical riddles. That's also fun, and it's human, and we shouldn't lose humanity. So please do that too. And well, that's it. Get into the habit of thinking about these concepts, okay? The goal, again, is not to formally define, properly and exactly understand every nuance, but to understand the principles, the guidance of thought that you can use to make logical conclusions, like predictability, noise, data set, mean, variance, blah, 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 blah. The tools to create the building. Let's continue. Fourth, selection bias. Let me see, what do you mean? I just explained selection bias. For example, selection bias is when you select a data set which is biased. For example, if you ask about, do you like golf? But you ask this in a golf camp. You know, if you go to a golf camp and it's like, hey, do you like golf? And most of the people will say yes. Otherwise, why are they in the golf camp? So you should ask, do you like golf? In the golf camp, in the tennis camp, in the football camp, football field. When you say golf field, well, you know what I mean. In the swimming pool, in the beach, in a fucking rocket in space, if possible. Just ask about golf, because we are in a societal experiment in different contexts. It's like selection bias, because it's a bias, like a prejudice that leans the truth or the perceived truth. That's a good, that's actually a good thing to think about statistics. Good model. Perceived truths based on repetitive evidence. I mean, that's science, actually. Yeah, but a good tool for doing science is statistics. Anyway, that's the fourth thing. Okay, so the third thing I tried to learn was like the data set matters. The fourth is like where you get the data from also matters. The fifth thing is correlation is not equal causation. This one is a very nice one. I'm gonna give the classic example of ice creams and people drowning, which is like, there is a statistical, this is true. Huh? You realize that when ice cream sales go up, the amount of people dying of asphyxiation or drowning, also go up. Okay, and therefore eating ice cream increases the likelihood, causes you to die out of asphyxiation or drowning. Is this correct? Well, not necessarily. Actually, it's not true. What happens is that there's like a hidden variable. That's the thing. That's how you call it. There's another name. I don't know if I have it here. Confounding variable. Confounding variable. I like the term hidden variable more. It's the same. But this is another concept. The concept of the hidden variable, of the confounding variable. What does this mean? Yeah, sure, this is true. There is a correlation. When this goes up, this usually goes up. But why? Because of the weather. When it's hot, people eat more ice cream. But when it's hot, people also go more to the beach. And if you go to the beach, it's not statistically likely that you're gonna drown, but if there has to be more people drowning, it's gonna be when it's hot, because people want to go to the sea, take cold water, and maybe some of them die from drowning. So yeah, it's true, there is a correlation. These two things tend to happen at the same time, but this doesn't mean that one thing causes the other. And this is the classic example. For example, let's mix two of the concepts we have learned. So the hidden variable here would be weather. The actual thing that is causing this is the weather. The weather makes people eat more ice cream, the hot weather, and also causes people to go more to the beach. And if you go to the beach, there is risk you die out of drowning. So you always want to ask yourself, is this just a correlation or is there a causation? And I'm going to give you an example of something. We're going to make an illogical conclusion out of not realizing there is a hidden variable and out of a biased dataset. Selection bias, we're going to mix the idea of a selection bias and the idea of a hidden variable. So let's say that we do a test about people who eat apples. Maybe it's not the best example. Do I have an example here? Yeah. No, apples is a nice example. Let's think about people who eat apples. And then you make the measurement and you realize that the people who eat apples have a 90% chance of getting cancer, right? Let's say that that's the result of your experiment. I mean, first of all, if apples are natural, something should feel weird. Like, wait, apples is a fruit, and fruits usually don't cause cancer, so why is this happening, right? Something should smell weird. And then you realize that in your data set, so to measure this, you have to make some people eat apples and then see if they develop cancer. What is the chance of that being correlated, right? Or even causation? And we reach the conclusion and we say in our study, yes, apples cause cancer or are very correlated with cancer. Now, what could be happening to reach these conclusions? Well, maybe you go to the study and you see the data set and you see that 9 out of 10 people in this data set were drug addicts. Okay, let's do a syringe here. Were very, very, really hard drug addicts. Cocaine, weed, alcohol, LSD, everything. 9 out of 10 people. And then, which is 90%, and only one person was healthy, or at least not drug addict. And that person didn't develop cancer. And this 9%, this 90% actually developed cancer. So why did you see in your study that people eating apples got cancer? Well, there was a hidden variable. The variable that 90% of the people you took from this study are actually drug addicts. So it's clearly a more statistically strong statement to say that, okay, actually, maybe it was not the apples, the ones giving cancer. So you not only had a hidden variable, but your data set was biased. So you had a selection bias. And you should have done the study in a larger amount of people. So the likelihood that you take 9 drug addicts out of 10 people decreased. The noise decreased, call it that way. I don't know if there's a more formal way of calling it. Well, the variance, but the noise is kind of like an interesting intuitive, right? Because if there's a lot of noise, you don't really know what's going on. If there's someone playing piano, but there's so much noise around you, you cannot really hear all the melodies so well, which would be like the analogy of the truth. Like, oh, I cannot listen to the truth because there's so much noise. That's a pretty intuitive way of thinking about it, and pretty accurate. So with this example, we can see that selection bias and the hidden variable or the confounding variable can lead to someone to misinterpret the results of a scientific study. And I'm going to tell you a dark secret, which is sometimes this is done on purpose to manipulate public discourse and win elections and put money in your pocket. I mean, not in your pocket, like in the one who is manipulating pockets. This happens. So if we want to reduce the possibility of this happening, we should all know how to detect and quickly all this bullshit. And that's how we get to an utopia, and that's how all this correlates to to a better functioning society. So please train your brain and train it, if possible, please, in these concepts because they are very useful in nowadays information era. Let's try to make it more white. Let's take a little rest. Okay, just while I erase the whiteboard. Cool. Correlation is not the same as causation. Next concept. Survivorship bias. This is an interesting one. I mean, all of them are interesting. So let's say, okay, I'm gonna explain this example. People who are successful wake up at 8 a.m. every morning. So if you want to be successful, you have to wake up at 8 a.m. every morning. I mean, you cannot wake up at 8 a.m. in the afternoon, but every morning, wake up at 8 a.m., read 20 pages of a book, and you will be successful because 80% of the people who are successful do that. So if you want to be successful, you have to do that, and you will have an 80% chance of being successful. Nope. Survivorship bias, it could be understood sometimes as a subset of the selection bias, right? If you only focus on the successful people, and you see that most of them wake up at 8 a.m., and therefore you conclude that to be successful, you wake up at 8 a.m. Well, there might be a correlation, but maybe it's not a causation, because for every successful person, okay, these are people, but I'm too lazy to draw the faces. For every successful person, how many unsuccessful people are that wake up actually at 8 a.m., but they are not success? I mean, you also have to define success, right? It's very important when you do study. Be very clear with the definitions and then do logical conclusions on top of that. Static dynamic, yes, same thing. So yeah, maybe most of the people who are successful, 80% of them, let's say, wake up at 8 a.m. But how many people which are not successful actually wake up at 8 a.m.? Maybe it's like, let's say there's like 30 people here who do it and are not successful, and here there's just 10%. 10 people. So from all the people, let's imagine it's only these ones. From 40 people, only 10 of them, and all of these wake up at 8 a.m., only 10 of them actually are successful. So we could say the correlation, probably not even causation, because in a successful people's lifestyle, there's a lot of things you can do. Not only wake up at a certain hour, eat some food, have some relations, there's so much variable, so much potential noise that you have to account for. So be careful when someone tries to tell you what to do or what you have to do with your life based on this kind of reasoning. Be very, very careful and very, very skeptical. More than skeptical, critical. But okay, bro, but then 10 out of 40, that is 25%. So if I do this, I only have a 25% chance of being successful, not really an 80%. That's significantly smaller. You were either trying to trick me or you were stupid and having, not in a negative way, but objectively stupid. Your conclusions were illogical. Your reasoning was flawed. You didn't have the whole picture. You had survivorship bias, which is some kind of selection bias. Why is it called survivorship? Because you only focus on the succeed cases, on the survivors, the one who passed it. So it's like, okay, so there is survivorship bias here, because I'm only focusing on the success, on the aftermath, but I don't focus on the overall population in this case. Now I have a question to myself. It's like the theory of evolution a very big example of survivorship bias? Because, for example, let's say a species developed some adaptation, wings, and that made them survive better, and now 80% of the, actually 99%, 99.999% of the birds have wings, and we can conclude that wings are good for evolution because it made them adapt better. But maybe you you are being, oh, maybe the whole theory of evolution is a very big survivorship bias. I don't know, maybe a very useful one, but a bias after all, because maybe there were lots and lots of species who had wings, and the ones who survived and passed the genes, well, yeah, they had wings, but maybe having wings is not the actual factor that made them adapt. Maybe it was another part of the body. So when you, well, that's something to take into account when you are analyzing evolution of species. Maybe you are having some, maybe there's a hidden variable, which is not wings, but other thing that made them adapt. And we are just having some survivorship bias in our sample, which is looking at birds. Yeah, that doesn't mean that the whole theory is a bias. It just means that when you are analyzing evolution, you should take into account specifically the survivorship bias and the potential implications of a hidden variable. For example, I've never thought about evolutionary science, but I mean, yeah, I've thought about it, but not in this specific part of it. Interesting. I don't know. Go search it up. That was an interesting thought I had right now. So survivorship bias, which is just this is the sixth thing. Let's go with. There's like 9 things I want to explain. Let's go. Let's see how much time. 1 hour. Okay. Sixth thing, seventh thing. Oh, the classic. When something is up or down, a very big percentage. Oh, something is up 100%. That must be a big increase. Well, no, because percentage is not quantity, is proportion. And if a quantity is big, doesn't really mean a proportion is big. Okay, there's better ways of explaining this. Let's just go through it. Let's go use black. Okay, the classic example is the murdering. Crimes, let's say crimes. There was 1 crime in the whole city yesterday. Sorry, in the last year. And this year there has been 2 crimes. Oh my God, the increase is 100%. Okay, to calculate the increase, you take the difference and you compare it to the starting point. And well, 2 minus 1, the difference is of 1, and the 1 is 100% of 1. So the increase in crimes has been 100% in 1 year. No, our society is being fucked up. Oh, what are we doing wrong? There's 100%, 100%, 100 is very big. Oh, but that's the proportion. The actual amount is 1. And now we have to figure, maybe if you even analyze deeper, you realize that this one was because, well, someone was having, I don't know, a schizophrenic attack, and he decided to go to the street with a machete and like, and killed someone. I don't know, it's just that extra one was that, and the other one was, I don't know, a crime. Someone stole a mobile phone. Something more. Let's put something less dramatic. Well, yeah, you can say it's 100%, and oh my God, 100. That's very big. Like, don't get fooled by big claims with big numbers. Think, because size is dependent on comparison. If I tell you 76, is it big? Is it small? You don't really know. Like, you need something to compare it to. You cannot use the logic of comparison if you only have one thing. Like it's like if someone was born and always saw the light and never saw darkness, how can he know that darkness exists? He only knows light. Like you need to use comparisons, and to compare implies in its meaning the existence of a change. And if you only had one state and never changed to the dark side, for example, you cannot compare. So if you have only one unit, well, I just cannot state anything about it with the logical of comparison, because there has no change. There's nothing to compare it to neither. So if I get 80, okay, now I can do there's more information. I can do more stuff. Okay, this is smaller. Now I can say greater, less than only makes sense if you have 2 sides of a thing to compare. Okay, if you only have one thing, you just It's an axiom. It's nothing you can do. It's like, okay, this is truth. Okay, this exists. And so what? 76. Yeah, 76. 76. Okay, that's it. You can't really do much about it. So don't get fooled by amounts. For example, this is gonna be, of course, I'm gonna get controversial here. I'm gonna create controversial thoughts on you. But with the tools I'm giving you, you should be able to be, intelligent enough to not have these conclusions, or at least if they are actually the conclusions, at least you can find better solutions. Let's say, well, no, let's just keep it this way. I already got controversial with immigration at the beginning, so let's just keep it as this. Crimes go 100% up, but the actual amount of crimes that are committed is just 1. And let's say, okay, it also matters. You have to compare it to what? Comparison to the amount of people. If the society is 2 people, okay, and you have 2 crimes, that means that, oh shit, for every person, there's a significant amount of increasing crime. But if the society is 1.5 million people, the chances that one of these suffers a crime is 2 over 1.5 million, which is ridiculously low. Zero point 1, 2, 3, 4, 5, 1, 3. Okay, sorry. 1, 2. 0.00013%. Very small. You don't really have to worry that much. You should live 1.5 million days in order for a crime to be done to you. Which 1.5 million days is 4,000 years. Yeah, you should live 4,000 years in this city if so you are statistically likely to get a crime on you. No one lives 4,000 years. In fact, they live 90 as much. Let's say that the average lifespan is 90. You don't really have to worry about this that much. Of course, it's better if we understand why the crime happened, so we can reduce. There's always room for improvement, and we should aim for improvement. Oh, 2 crimes, let's see why. Let's try to get it to 0 next time. But the proportions, the comparison tool is useful for prioritizing, okay? Prioritizing. If we know that crimes are so unlikely, but we also know that, let's get dramatical. Suicidal rates are, let's say, 1%. Each year, 1% of the population. Well, we should prioritize. We should prioritize looking for a solution for suicide rather than less crime. But that doesn't mean crime is not important. It's just comparison is a useful tool for the prioritization of problem solving. But comparison should not be used to say that a problem is not a problem, because that's a definition thing, not a comparison thing. So crime is a problem and suicide is a problem. Now, which one should we tackle first? Well, if we can, we tackle both. But if there is a limitation of resources, well, we should tackle first the one who is more statistically likely, probably, or more important. Maybe there is a culture that doesn't really care that much about crimes. So I'm getting theoretical and very abstract here. So maybe you should prioritize suicide in that culture. Or maybe we have a culture that, let's say, makes all people... this is a very fucked up thing. Imagine a culture where old people are considered useless. And it's trendy that the old person decides to suicide for the better good of the society. That's very fucked up. But imagine that culture. In that culture, maybe they don't give a shit about this high statistical rate of suicides because it's a cultural thing from old people. So they focus on crime. It depends on a lot of variables. Again, you have to maximize your intelligence so you can see the variables and prioritize what you and what the group needs. Sometimes you should prioritize one thing, sometimes you should prioritize the other, But as you can see, there's lots of variables: culture, mindset, personalities, statistical analysis of what is actually going on. There's just too much. It's difficult, and we are not used to it. We're not educated for it, and we should be. Like I'm trying to do. I'm trying to educate people on the tools to actually build a better future based on reality, which is context dependent and also personality dependent. Blah 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 blah. So if you're an old person and you feel useless, don't do it. Please don't do it. Like old people are nice. You can just take care of kids or be there and be nice and smile. Just smiling to other people is actually useful. You're old, maybe you cannot move, you're in a wheelchair, but if you smile to someone, that's contagious, and you're doing good to the world. You see a young person there, and you smile to him and you say hi. You're already contributing to the world in a nice way. So if you are old and feeling useless, just don't do it. There's things you can actually do even if you're in a wheelchair, which is smile to people. That is really useful. Yeah, that can make someone's day brighter. I hope this compensates for my extreme examples because it's actually true what I'm saying. And I don't think there exists a culture nowadays that has this mindset about elderly people of, yeah, let's use suicide. No, what the fuck, man? Oh, we are social animals. We can always find usefulness things in others. Okay, let's go with the next example. How do I know this? Because I train in a calisthenics park, and I used to train in one which is next to a residency for old people and next to a kindergarten or a school, primary school, and it's such a nice place because you see how long is it the video? Maybe I don't want to get much into anecdotes. Let's continue with. Let's make a little pause. And you see the old people, you see the young people, you see all the stages of life. You see the young people training in the calisthenics. There's also a street of bars in front of you. You see the young people hanging out, training, elderly, kids playing around. It's such a beautiful place here in Barcelona. And you see the old people and they say hi to you and it's like, oh, good job. They see you doing the handstand and practicing and they are very nice. You know, they are in the wheelchair and they cannot do much about it, but they can cheer you up. They can smile to you and it's nice. It feels good. And that's how I know this. Yeah, there's like this granny. Her name is Anna, and he's like always cheering me up when I do something. She's like there in the wheelchair, like, oh, very good job, guy. It's nice, it's nice. Okay, anecdote time. Oh, you also see the kids playing. They try to copy what you're doing, and then you teach them. It's a very nice place. I love it. Well, let's continue. This is the 8th thing. Try to use rationality. Don't get too fooled by emotions led by big numbers. Always compare, always be more critical. If the situation is not very extreme, if it's a life or death situation, as we saw in previous classes, it's not like, oh yeah, is the lion gonna eat me? Of course it's gonna eat you, it's a lion. But society nowadays, it's super complex. As we can see, there's just lots of bad decisions being taken on emotionally driven people taking emotionally driven conclusions instead of based on statistics and actual reflections of reality based on measurements. So let's go to the 8th thing. The 8th and the 9th thing are pretty much a bit technical. Why would this be useful? I don't know why I added this. I don't know if it's that useful. I mean, it's good, of course, more knowledge, especially about statistics. In the modern era, it's not going to hurt you. I'm going to explain it. I don't know why I added this 8th point, which is, how can I describe it? False positives, okay? But why? Why did I? I mean, okay, let's go with it. Let's say that there's an illness with the chance of appearing of 1%. And let's say that This is the real one, okay? This is the reality. This is not in the experiment. Let's just assume it's 1%. And this is our measurement. Bada boom. And you test it on 1,000 people, okay? This is a detection tool to detect if you're ill. And you discover that your tool accurately detects the illness 99% of the time. Okay? That means that if you use the tool in 100 people, 99% of the times it will be correct. So there will be one person who will say it's correct, but it's actually not correct. He's not ill. It's a false positive. And in the group of 1,000 people, 1% of 1,000 is 10. Yeah, 10 people. So in this test, there were 10 people who were identified as ill, but they were not ill because of, well, just or maybe some random noise. Maybe the detection tool is not accounting for a specific chemical in your blood, which actually makes this whole thing go brrr. For complex biochemical medicine reasons, there is a 1% chance of this. If you're a doctor, you study these things. I don't know if a doctor or if a biochemist, I don't know, it doesn't matter. If you're a scientist or someone really, really specialized, you will care about these details and you should seek for these details. But in order to understand the statistics, let's just keep going with this reasoning. So 90%, 10 people ill, but they are not ill. That's a false positive, one false positive, because it's like, oh, positive, you're ill. Not in positive in the sense of, yeah, nice, I'm sick. No, positive in like, yeah, bro, the result was correct. And the correct thing, this is a very interesting thing. Correct and incorrect is not the same as good and evil. That's another whole topic of discussion that I will discuss in future classes. But yeah, cool. False positive. So if you get, for example, oh yeah, you're sick. Oh, maybe you shouldn't get very worried. I mean, you should worry. Of course, you should worry, but maybe you are part of that 1%. So if you, I mean, doctors know this. Okay, you don't have to worry about this. I don't think so. You shouldn't be. I mean, if your doctor is good, he will know this, and he will know that there is a chance that this is a false positive, and they should test you again, maybe with a different test, maybe with the same test, and then they can actually conclude, hey, man, I'm sorry, you get cancer, like whatever, or another illness. But yeah, I don't know why I put this thing here. Why is this useful? I mean, it's useful for yourself, of course. More knowledge is better. And why did I say this at the beginning? Because of the because actually from these 1,000 people, sorry, let's pay. Yeah, from these 1,000 people, 10 will be sick. Yeah, I mean, and then 10 people, which are the actual, because there's a reality that 1% of the people are sick, so 10 people will be sick, and 10 people will be falsely marked as sick. So maybe there is an overlap between these groups of 10 people. You know, maybe there's an overlap, maybe there is not. And this is more advanced. I don't know why I added this as. Well, there you got it. Just be curious, research about this. I don't really know why I did this. Ah, it's not the best example, but yes, I get it. I remember now with the immigration thing. Like, oh my God, 80% of the criminals are immigrants. That's like a positive state, positive in the sense of correct. That's a correct statement, but how many immigrants are there? How many patients are there? It's as an analogy with the medical thing. Like, okay, yeah, 80% of the criminals are immigrants, but how many percentage of the immigrants are criminals? That's a different question. And that's what matters when you're considering letting more immigration or not in your country. You should consider how many percentage of the immigrants are criminals, not how many percentage of the criminals are immigrants. Both are useful questions. Both have different meanings, but they are not the same meanings. Okay? So you must understand and be able to have a logical and quick intuition and realize that these questions are different. These measurements can have different logical and useful conclusions. And a lot of people are confounding this nowadays. Right? What is called right? I don't like to use right wing, left wing, but right wing people think immigrants are criminals, and we shouldn't let immigration in because of criminality. But then you look at the data, and yes, it's true that 80% of the criminals might be immigrants. These are numbers made up, but it was a high percentage. Now, I don't know if that study was correct or not. You should go check the study, how it was done, what was the sample, all the tools I've given you, all the frames to actually see. But let's assume that it was 80% of the criminals were immigrants, and that, but maybe just 1% of the immigrants are criminals. And well, that just means that from every 100 people that you let in, one will be a criminal, which is not a lot. I mean, of course, if, as I said, it's a matter of priority. If we can reduce this number to 0, better. But what should we prioritize, right? Immigration policies or policies against criminals, making criminals stop making crimes? These are the different questions or priorities that the different data sets are telling us, and we should be able to distinguish them. If this number was very high, like 99%, okay, there is a correlation and probably a causation of immigrants and criminality. But here, if these two are true, you cannot conclude that the more immigrants, the more criminals. Yes, sure, but only one on every 99. Okay, so it's not super crazy influence, and maybe you should focus on making criminals disappear, whether they are immigrant or not immigrant. Like, for example, put them then in prison. That's the simplest one. Or social integration of criminals. Give them something to do, give them a job, give them meaning so they stop being criminals. Different psychological techniques you can use to reinsert people in society. This is an important statistics to all these kinds of discussions. This is an important statistics to the how much immigration should we have discussion. But if you mix them, you can reach the illogical conclusion, assuming this is true, this data set is true, that the immigrants are the cause of criminality. Maybe the cause of criminality is that your law is wrongly written and you allow criminals on the street, or you don't properly make them become actually decent citizens. Yeah, so that's why it's important to understand. And as I said, these were assumptions. I don't know if the data says that. Assuming that the data says this, these are conclusions you can make. And now what you should do as a responsible citizen, and with all these tools, and first get used to using the tools, and then you go to a real example, to a real problem, and see if it actually is a problem, or if the solutions that someone is saying to that problem actually make sense based on real data. And you can also go to the data, to the study, and see if the data set has some bias, survivorship bias, selection bias, all we say. If they are using the mean incorrectly, if they're using the mode incorrectly, if they are using the units incorrectly. In the case of immigration, the units are a bit difficult not to measure. Like, what's the unit of immigration? One person. Person units, whatever. But this is what I mean. This is how we can improve society, and things that a lot of people get wrong. A lot. That's why it's important to explain it and to learn it and to get used to it. And I recommend you to start doing examples with something that is less emotionally charged in society, like dick sizes. That's funny. You can look at studies of dick sizes and take conclusions. Oh, what happened? It stopped recording? No. Oh, I heard like a clickling. Okay, maybe the phone runs out of memory and stops the video. So yeah, you should maybe start analyzing cases that are funny, interesting, and stuff like this, and not politically charged. And then after you have developed, you have strengthened your muscle, so you are not fooled by other people's mistakes, or fooled actually by people who are trying to manipulate you. It depends. I'm not saying all politicians try to manipulate you. I think there are politicians who are trying to be honest, and they are just stupid and making stupid decisions. Stupid not in the sense of as an insult, but as an objective logical conclusion, like, hey, you are having an illogical conclusion, therefore you're stupid because of this statistics. This sticks. It even rhymes. Next and last, the ninth example. Significant is not equal important, and non-significant is not equal not important. When you read something in a statistical thing, it's a significant measurement, it doesn't mean it's important. They have different meanings in this realm of knowledge. What does it mean, significant? Well, this is going to be part of homework, okay? It's something related to the p-value. I'm going to explain it, kind of, but it's better for homework. This is something we said at the beginning of the video. The coin flip example. We assume, this is our assumption about reality, that the coin is fair. Therefore, if it's fair, there's going to be an equal distribution of all the outcomes if you define fairness like that. So there's 50% chances of heads and 50% chances of tails. Now we start our experiment with our assumption. We throw the coin 100 times, and we get 80 heads. That's a lot. That's like 80 out of 100. That's 80%. Shit. 80% chances of head. But what we thought reality was is 50%. Okay, now we figure out what are the chances that this happens given our assumption. I think that's how you properly define p-value. I'm not exactly sure, but I'm going to write it here, okay? Understanding p-value and how it drives scientific agreements and discoveries. Or discoveries, they might be the same sometimes. Let's not get very detailed. You will figure out the details on your own. This is the principles, the guidance. So you see that you throw this 100 times and 80 of them are heads and this. So what are the chances that this happens? I'm not gonna get into the math, okay? I'm just gonna tell you that this is this way. Every time you throw a head, it's 0.5. Okay, every time, if this is true, every throw, there's a 0.5 chance of being correct, heads. Your prediction being correct. This was explained like shit. Every time you throw a coin, there's a 50% chance, assuming that that is reality, it might not be reality, assuming that this is reality, that this happens. So if you throw it twice, you actually have to multiply the numbers. Why? Okay, that's more technical. I'm not going to explain it because the video is getting very long. You should be curious about it and you should go and understand why this is the case. And you multiply it. If you throw it 100 times, you multiply it 100 times. Multiplying something multiple times is just an exponent. 2 to the 4 is 2 times 2 times 2 times 2, 4 times. So if you want to know the chance of throwing 80 coins and all of them are heads, is 0.5 to the power of 80. And if you do this calculation, that's crazy small. The chance of this happening is 0. Now we have here 24 zeros. Imagine there is 24 zeros and then 8 to 7. Very, very small. So, man, we've done an experiment, assuming this is true, and the result we got is this unlikely. So maybe we are wrong. You know, this is where you should start suspecting, like, maybe my assumption is wrong. Maybe maybe this coin is not fair. Maybe this coin is biased for whatever reason. Now you have to get creative and analytic and see what's the reason. But we can conclude that this coin is not fair, because this is very, very unlikely. Like, you should be throwing coins. For this to happen, you should be throwing coins for longer than the universe. I did it for just 100 times. That's not longer than the universe. I did it in what, 5 minutes? So you should start suspecting. So that's important. That's why p-value is important, because it's a nice, let's say, a nice limit on detecting if you are actually being biased by some kind of hidden variable, some kind of noise, some stuff, or you're actually facing some truth that opposes your beliefs. This will be your belief, your assumption, and this is the experiment that is telling you, hey, maybe your belief that this is equal to 50% is not true, because if this were to be true, the chances of what you just witnessed, because you witness it, is very, very low. So this is a bit more complex to understand, but just go to AI or some videos and get used to it. Why is this important? Why is p-value important? Because it's some sort of agreement threshold. For example, in physics, the p-value to agree on a discovery is very low. In psychology and more social sciences, it's bigger. Don't quote me on this, but I think in psychology it's like 5%, and in physics it's like 0.000000000, a lot of zeros, 1 over 3.5 million, I think it was. I checked with ChatGPT a few days ago. So in physics, if you measure something and giving your assumption about physics, that's how the Higgs boson was discovered. They did their very intelligent people experiments with the particle collider and all this stuff, and they were like, okay, let's assume the Higgs boson, which is a subatomic particle, I think, or a particle, whatever, a particle to explain some physical phenomena of the very, very intelligent physicists, whatever. Let's assume it's real, or let's assume it's not real. Let's just have an assumption. What is the chance that what we have observed with colliding particles happens? Oh, the chance of this happening is, or not happening, is so small that it must be true. Therefore, the Higgs boson must be a real or a scientifically based theory of reality, and say it that way. I don't know exactly the details, but that's the thing. And for example, with psychology, maybe it's like, this was like 0.0000000. So what we measured, given the assumption of not existing, the Higgs boson would happen with such a small chance that it must be like that our assumption is not true. So not is true. I don't know if this makes sense for people. So if you've done math or logic, this is very obvious. Like, if A is equal A, not A is equal not A, and if not A, that means that not A is not true. So not true, not A, not A, that means that not A is not. So if not A were to be true, fuck, this is mindfuck. Okay, now this became a logics class. Not goes to true. Why? Let's try to explain it, because now I'm getting frustrated with myself. How much time do I got? Okay, so you got not. Okay, you're getting the idea of not. Imagine this means not A. What is this equal to? Let's put X. We don't know what this is equal to. So if from the assumption of A equals A and not A equals not A, from this assumption, we can conclude that if we had only the inner part of the computation, not A, should be equal to X, given our assumptions, these are beliefs that we create, axioms, what would be X value? What would be not A, right? Because based on our beliefs, not A is not A, so X should be not A. X should be not A. But this is not what this equation is doing, okay? This equation is adding a not on that. So, what's the logical, intuitive way to do this jump? If you got not A, So it should be the opposite. I think I'm missing an axiom to explain this logically. But which one I'm using? I mean, if you apply not to A, it becomes not A. It becomes the inverse. Oh, I think, oh man, I'm getting into deep shit. I mean, for me, it feels nice, but I know that if you've never done logic, this feels like, what the fuck, then why it's A equal A? Because not just goes to the previous operation. Oh, okay, I get it. No, you don't really care. You don't need another axiom. Ah, shit. We got it. Don't worry, guys, I'm back. Not A is anything. A from anything. I'm making it up. So not something equals not something. So you got not something. This is the something. No. Oh, fuck, what's going on here? Oh, why is this true? I mean, I know it's true because, well, statistical observations during my whole life, but logically, why is this the same? Not A equals A. Oh shit, guys, I'm having a brain fog right now. As you can see, everyone's learning, everyone has little gaps of understanding that you can just fill up while you are curious. How do you compute this? Yeah, this is obvious. Like, no, that's I'm just following an obvious, always true statement. How can I do this? I think I have to define another thing. Yeah, maybe I do actually need to just assume that not A equals A. Maybe it's just another. I don't know, guys. If you're curious about this, or if you know the answer, I'll look for this when I finish the class because I'm actually curious. What is the most logical, intuitive transition from these statements so they're true? Is it am I missing an axiom? I am just stupid. You see, I'm also stupid sometimes. I don't know all the answers. I just try to explore and be a curious motherfucker so I can better move through life. Okay, anyway, let's go back to the p-value. There's just research about it. Okay, it's actually a distance from the from the variance, no, a proportion from the times the variance thing, which is considered as a new discovery. That's the thing, I don't want to get too technical in this video. I want you to see how it feels, to see how it looks, to think on statistical terms and to try to figure things out. That's the thing. Not pretending to be a math teacher, pretending to be a critical thinking teacher with different examples. And one of very good tools in the era of information is statistics. So please research more about p-value and stuff like this. That's part of the homework. And oh, you can also think like an engineer, break down the p-value in different concepts that you might want to understand first and then build it from the ground up, as we saw in previous classes. So this is the homework, okay? Once you've been faced with multiple sets of data where you have to do statistical deduction from it, you get used to it and it starts to feel intuitive. But until you get to that point, it's useful to have a checklist of questions, so you can make sure you're not falling into any of the biases or statistical illogical conclusions that we have been explaining through this class. So what is the set of these questions? Like, what questions should I ask myself to not be falling into the biases? Well, that's your homework. You can ask ChatGPT about it. It's pretty good because statistics has been around for lots of time, and AIs have lots of information about statistics, so they are probably going to guess it right. And if they don't guess it right, you already have the tools to start thinking around it and well, just creating it. That's kind of it. Go do a checklist of questions, write down your checklist of questions. Like, for example, with the survivorship bias, is my sample big enough? Is this sample biased by a hidden variable? This kind of questions. Just go and create your own checklist. And the best thing you should do is create a checklist, train with different exercises, not only in one afternoon, different afternoons, train with different exercises. And yeah, just get your brain used to this kind of thinking so you can ask better questions, so you can actually see reality as it is, or more equally in the shape it actually has, and just make better decisions and lead society to a better world and yourself. Yeah, that's the homework. And after you've mastered this, I would encourage you to question studies, to question important things that are important to your society, like these trendy topics of immigration, sexism, criminality, and all this stuff. That's it. I'm gonna give it a last try, because now I'm like, I want to solve it. I want to understand that. What time is? How much long is this? Okay, it's fine. Let's just do it. Let's try to understand the not A shit. So if we know that A equals A, and we know that not A has to be equal to not A, what can we know about not A? What is this equal to? What am I missing? What am I fucking missing here? I feel so stupid. Yeah, this is just logic. This is just an always true fact. I'm missing something. If not false, if not false, so okay, I have to assume something like if A is true or if A is false, and then derive from that maybe. Oh fuck, my brain is not working. You know, this is why I like mathematics. It always, this is actually brain training. You know, like when you train your biceps, you lift this. When you train your brain, you just sit. Now I'm standing up, but you just sit and think. And maybe you go explore something. You talk to a mathematician, like, "Hey guys, can you make a logical, simple step to figure out what x is like here?" Let's give a value to see if we can get to, let's say 0. And let's say that we have the possible sets of 0 and 1. So if a is not 0, not 0, what is x? Given this set of values. So if it's not 0, it must be 1. And if it's not 1, it must be 0. Therefore, x is 0. So maybe this operation, I'm defining a function, I'm defining an operation under this set of values. But what if you have 0, 1, 2, 3 values? Then the idea of truth and falseness, it's kind of false or breaks apart because you have more than 2 states. Interesting. So, I mean, this is like a proof, I guess, to say that not A is A. But we are having another axiom, which might be that we are working in a set with 2 possible values, maybe. I don't know. This kind of makes a bit more of sense, but I'm not sure. I'm not a mathematician. I'm a computer scientist. That's why I took the 0-1 binary example, of course, like them. this is my bias, you know. So maybe this is not the definitive truth for showing that not A equals A. Maybe there's a better explanation, and I'm just being biased. I should repeat the experiment. I should go to someone who is a mathematician, someone who is a physicist, who has also some formal training in logic, and compare the reasoning process and get to a deeper truth. Exploration. In this case, intellectual exploration. All right, this is the end of the class. Hope you liked it. Not missing anything. Not missing anything. Thank you, Shifu. You're always so helpful when Capybara is not working. What the hell, man? I thought it was charging. Damn. All right. Oh, no, not working. All right. Ciao, ciao.